Hello. In this short lesson, we'll be looking at factorial analyses of variance. You'll remember that some time ago we looked at one-way analyses of variance where we have a continuous response and different levels of a single categorical predictor. We also went on to look at two-way analyses of variance where we had two categorical predictors and a continuous response. And I mentioned briefly that we can build simple models with the different levels of one predictor and the different levels of another predictor. But then we can also add an interaction term for the complex way in which the individual categorical predictors might interact to influence that response. Let's have a look at this interaction term here within the general linear model framework. What it says is that for this particular combination of fertilizer and pesticide, we should have a certain adjustment delta. And for this combination, 1 and 2, we should have another adjustment delta 2, and so on and so forth. The null hypothesis in these cases is that all of these adjustments are the same, i.e. that there is no real interaction going on in terms of the effect of these predictors on that response. Let's have a look graphically what we mean by an interaction. So let's say we've done an experiment in which we have varied the levels of the fertilizer. We have A, B, and C, and we have a response yield. And let's say that these points more or less represent what the population means are, so they're pretty reliable. So here we can see that fertilizer B produces the higher yield when at least we have pesticide 1 applied. But when we have an interaction, the effect of this fertilizer on yield depends on the level of this other categorical variable, in this case pesticide. So it might be, for example, that when we have pesticide 2, here B is no longer the highest yielding fertilizer, and in fact it's A. So interactions occur when the effect of one predictor variable on that response is influenced by the levels of another predictor variable in the model. So it's something more sophisticated and conditional. I now want to look at the factorial analysis of variance design. And we'll do so by looking at a simple experiment where we have sowing rate and variety. Let's say we've got 4 types of sowing rate of a seed and 2 types of variety of our wheat. Now, if we were interested in sowing rate and variety, there are a number of different designs we could think to develop. But here is one that would be particularly informative. So we've got 4 sowing rate combinations we're interested in and 2 varieties. Of course, and here the numbers I should say are the replicates of each of these different combinations of our predictor variables. Of course, if we were interested in variety, we might spend a lot of effort looking at just this sowing rate here or just this one here. Or if we're interested in sowing rate, we might want to look at just one variety rather than both varieties. But in this case, we can actually look at both the effect of variety on yield and also the sowing rate on the yield, and actually look at the interaction, because it may well be that the effect of variety is important in that V1 gives a higher yield, for example, but only at these sowing rates and not at those sowing rates. So this type of design allows us to investigate interactions, i.e. when the effect of one predictor variable on the response depends on the level of the other. We've got things covered because with this simple design we've got all of the combinations nicely evenly matched. It also means that any given observation can be used in not just one comparison, for example between varieties, but also across the way here between sowing rates. So with this design, we have what's called hidden replication, in that our observations are being used in several ways when conducting our analyses. This is, of course, a factorial design, and in fact, it's two factors. Here we've got variety and sowing rate, and it's a 4 times 2 level. So we've got 4 levels of sowing rate and 2 levels of the variety. Now let's have a look at applying a factorial analysis by using R. And here are the data that we're going to be looking at. This is from Sokol and Rolf, a really nice biometry text. And it's actually looking at the consumption of male and female rats of different types of lard, whether it's fresh lard or rancid lard. And what we can see here is that we've got a factorial design and that we're interested in looking at the sex of the rat, but we're also interested in looking at the state of lard. And we can examine sex and lard and their interaction if we apply the appropriate model. So let's first enter our data such that we can use it in R. And because it's a simple list of data, then I'm simply going to write it out. We've got our consumption data here for 709 all the way down to 539. We've got our sex. We've got 3 males here. We've got 3 females here, 3 males and 3 females, and so on. And then we've got the state. I've called it tasty, whether all of these are fresh or rancid. So we've created 3 vectors, one for consumption, one for sex, and that varies male, 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 and then female, 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 and so on, and one for the state, which I've called tasty, which is 6 freshes and 6 rancids. And that collectively represents this entire data set. Now, how do we fit a factorial analysis of variance? Well, with a factorial analysis of variance, we're looking not just at the main effects, but also their interactions. And so here we're fitting a linear model with consumption and sex times tasty. You'll remember that the times represents fit of a model with interactions, and it knows straight away that sex and tasty are both categorical variables that have been defined in that way, and we can plot out our results. So what do these results indicate? Well, I find it particularly useful to start at the bottom and move from interactions to main effects, because if your interaction is significant, then it's clear that those predictor variables play some role in affecting that response, whether or not those predictor variables are significant as main effects. But in this case, there is no significant interaction in that our p-value is relatively high. We would get that outcome or a more extreme in a high proportion of cases, even if the null hypothesis of there being no interaction were true. But we can say that there's a significant effect of lard state in that our tasty predictor is highly significant. And there is no significant effect of sex on the consumption of the lard. Now, have a look at this design with regard to the amount of replication. We had 3 replicates for each of these combinations. Is that just a pretty thing, or does it actually matter to the analysis? Well, it really does help interpretation in the analysis if this experiment is what we call orthogonal or balanced. And by that I mean that we've got equal replication for each of the treatment combinations. Let's revisit this issue of orthogonality. 2 categorical variables are orthogonal, i.e. they're not associated with one another and they're not collinear, if knowledge of one provides no information about the other. So for example, if we knew the sex, we wouldn't be able to guess what state of lard that sex individual was actually presented with. In a factorial general linear model, the 2 factors are orthogonal if the same number of observations are made for all of the level combinations. Why is that important? Well, in those orthogonal designs, The type 1, type 2 and type 3, and we've met two of those, the first and the last sums of squares, are all equal. And so interpretation is easy. And that is because our predictor variables are not collinear with one another. They're not changing as we change the other. And it makes our interpretation that much easier, and that we don't need to think about an alternative interpretation based on an alternative partitioning of the sums of squares. We like easy, and so it's important where possible to strive for equal replication in these factorial designs. So we know in this case that we have a balanced design. We've got three replicates for each of the combinations of sex and state of lard. But how would we fit a type 3 sum of squares model to data if our design wasn't completely orthogonal and we really wanted to, even though it's a bit of a silly thing to do when we've got interactions, but whatever, we'll still do it because that's the default. How do we want to do that? Well, here's how we could do it. We could load the library car, which has a type 3 sum of squares option. But here's the important thing. When fitting models using this particular option within car, we need to reset the contrasts. The typical contrasts are treatment contrasts, but here we need to set them to some contrasts for rather technical reasons, and later on we might get into contrasts. Here is the fit of the model again. But this time we're actually going to look at it in terms of running a type 3 sum of squares using the ANOVA function with capital A. And you'll see that we get precisely the same results for our particular data because our design was perfectly balanced. Thank you for listening to this R Labs tutorial video. If you found this useful, you might be interested in our free online Moodle course, or check out and subscribe to our YouTube channel.